Today we are going to talk about limits of functions. So we have already talked about limits of sequences. So now we're going to define the notion of limit of a function. And if we make a quick review of a little bit of what we have done in the course so far, we first saw sequences and studied a lot of properties of sequences, limits of sequences, limit laws, subsequences, infinite sub, and so on. And we thought that we can use sequences to define the notion of continuity. So we actually defined continuity a few lectures ago by using sequences, and we didn't say anything about limits of functions. We haven't defined them. So we can define continuity using sequences, and then we thought that this is equivalent to this epsilon delta characterization. We showed some laws, and last class you saw the intermediate value theorem and the extremal value theorem. These two theorems have hidden inside of them the completeness axiom, since they are telling us something about the fact that R is complete. And our goal is to eventually, so now we are using what we already know about sequences and stuff to study the theory of functions, which is part of what we want to do in this course. To start the theory of functions, we started with continuity, and we showed some properties about them, these two being the most important theorems. And after studying continuity, we want to get to the topic of derivatives to give a rigorous treatment of derivatives. And to be able to study derivatives, we also need to define rigorously the notion of limits of a function and have a little bit of properties of limits, since we need limits to be able to define derivatives. So today we'll talk about limits, and there are several types of limits when we are talking about functions. We have ordinary limits, we have lateral limits, we have infinite limits. This is a little bit how they look like. For an ordinary limit, we can imagine a function whose graph looks like this. Let's say we want the limit of a certain function. So now we need to specify where the value of the function is converging to. So when x goes to 3, we want to know the limit of the function f. So for the ordinary limit, in this case, it's equal to 1. You are getting closer and closer to 1. The function does not need to be defined here, and it could be defined and be anything else. It doesn't matter, the limit is still 1. And it's ordinary because you go in both directions, left and right. For the lateral limits, the left-handed limits and the right-handed limits, you can imagine a function whose graph does something like this. So lateral limits means that you take the limit only when you're approaching, say in this case, you want to approach 3, you can approach 3 to the right of 3 or to the left of 3. And in this graph, if you're coming from the right of 3, we are in this area. In this area, we are in this part of the graph. And if you're approaching 3 from this part, your function is approaching here the value of 2. So the lateral limit from the right, which we denote by this plus, of this function f is equal to 2. And if you're approaching from the left, you're in this side, we are in this part. So we follow this graph of the function. If you're getting closer to 3 from the left, your function is approaching 1. So the limit when x goes to 3 minus of f of this same function f is going to be 1. Well, in this case, you can, of course, still take the lateral limits, and both the right and the left limits are still going to be 1 in this case. And in this case, they can also be different. So in particular, if the ordinary limit exists, then the lateral limits also exist and have to be the same. But the lateral limits can exist, and they can be different. And in that case, the ordinary limit does not exist here. So ordinary limit does not exist in this example. Well, in this case, lateral limits coincide. And for infinite limits, this could look something like this. You want to know the limit of a certain function. Let's say this is a graph when x goes to infinity. So your x is getting bigger and bigger here. And as your x grows, your function is getting closer and closer to 4. So this is your limit when x goes to infinity is going to be equal to 4. So this concept might be familiar, and the goal today is to give a rigorous treatment of them, to give a rigorous definition, and see how we can make the differences for the 4 types of limits, but see how also they also behave very similarly. And we can actually give a very general definition. It's not a very standard definition, but we can give a general definition that encompasses all of these cases, which is what the textbook does. So we're going to follow this. Right now we are in textbook section 20. So you want to follow along. So now let's move with this in mind, that this is the types of limit that we want to capture. Let's move on to how to rigorously define them. And just like we did before, where we defined continuity using sequences, we're going to take advantage of everything we know about sequences to we're also going to use sequences to define limits of functions. And then we're going to show that there is also an epsilon delta characterization to define them, but it's generally easier to work with sequences. We're going to use sequences to define the limits, and we can do that in a very general way. So let's take a look at the picture and see how we can think about it. We want to think of the idea that your x here is getting closer to this variable, and that your function is getting closer to this value. And as we already saw for continuity, we can formalize this idea of getting close by considering a sequence that's converging to 3. So your x is going to be a sequence converging to 3, and then your values have to be a sequence converging to 1. So this is what we can do. We want to consider all of the cases simultaneously, and here's how we can do this. So let's consider a subset S of the real numbers. This subset is capturing the idea of the different possibilities here. So for the ordinary limit, we want to consider basically everything except this, while for the lateral limits, we are going to consider only a subset here to the right, an interval to the right for the right limit, or an interval to the left for the left limit. All of these possibilities are going to be considered by this subset S. Let A be a real number, or symbol plus infinity or minus infinity. That is the limit of some sequence in S. For example, A could belong to S, and in that case, we already satisfied this. And let L be either a real number or symbol plus infinity or minus infinity. So we have many possibilities. A can be a number, or A can be plus minus infinity. L can also be a number, and it can also be plus infinity or minus infinity. We're considering all of the options once. And in any case, we write that the limit as x goes to A in S, this S is the subset of f of x is equal to L if, so first, f is a function defined on S, a real variable, real valued function. And here's the important part. For every sequence xn in S with limit a, so a is this a here, which could be a number or plus infinity or minus infinity. We have limits. So we're talking about the limit of a sequence. So we have f of xn converging to L. And here we're talking the limit as n goes to infinity because we're talking about sequences. So we can actually define limits on functions in all of the cases by using sequences in this way. We can read this as the limit of f to x as x tends to a along S. And some important comments here. Since we are defining here limits using sequences, and we already defined continuity also using sequences, the definition looks very similar. Note that the function f does not have to be defined on A. F has to be defined on S, but A doesn't have to belong to S. A just has to be the limit of some sequence in S. But in the case where A does belong to S, the function f is defined in A, and our definition of continuity using sequences, from the definition, it immediately follows that f is continuous at a point in the domain of the function that's S. So if the domain of your function is S and this point belongs to the domain, this is true if and only if the limit as x tends to a along S of f of x is equal to f of a. Because if your function is continuous, if you have a sequence converging to a, then your values converge to f of a. And another important point is that if the limit exists, then it is unique. There can only be one possible value of L. And this is true in all of the cases. And the reason this is true is because we know that this is true for limits of sequences. We already proved this. So this is true because we showed that limits of sequences are unique. This is the general definition, which is non-standard. It is used in the textbook to cover all of the cases. Now let's say the standard definition of the limit of the different types of limits. Let me copy this. So these are the standard definitions. So for an ordinary limit, for a point in R and a function f, we say that the limit when x converges to a of f of x is equal to L if, under the definition that we just gave, the limit of x going to a along S of f of x is equal to L. What we need to do is to say who has to be S, and in order for an ordinary limit, S has to be some set equal to an interval around A. Except for the point A doesn't have to belong to the set. So where J is an open interval containing A. If we take a look here at the picture, your J could be something like this, and your set A, your set S is everything except 3. So 3 belongs to J, but 3 doesn't belong to S. So this is called also the two-sided limit. So your function f, the reason that we remove a from the set is because we are saying that the function f does not have to be defined in A, and even if it is defined in A, it could be something completely different. So the only way that this is actually equal to f of A is in the case that f is continuous, which is not always. Now similar for the right-handed limit. You have a real number a and a function f. Then we say that the limit when x goes to a plus of x is equal to L. If, and we can use again the previous definition, if this is true for our previous definition, that is using sequences belonging to S, we have to say who is S. So for some set S, for some set S equal to an open interval starting at this same point A, so same A here. This means that their interval is something that's to the right of A. So we'll take a look at the picture here. Your set S is going to be something that starts here at 3 and any interval here from A to B. This is A, this is B, and this is to the right because your interval is to the right. So an open interval starting from 3. Similarly for a left-hand limit, again for A in R and the function f, we say that the limit as x goes to a minus of f of x is equal to L if we have, let's copy this, for some open interval. If we are in the right, we need some open interval starting at A. If we are on the left, we need an open interval ending at A. Which means that you are to the left of A. Look at the picture, your interval is going to be something like this, that's ending at 3. And finally, for infinite limits, again, the only thing that's changing in all of the definitions is who is our set S. And if we take a look at the original definition here, what's the role of the set S? The set S appears here especially. That for every sequence in S, you have this. So this is like the domain where you take your sequence. If you can take your sequence for any interval around A, then it is a two-sided limit. If you can only take your sequence of points in an open interval to the right of A, then it is a right-hand limit. And if you take your sequence of points in an open interval to the left, then it is a left-hand limit. This set S tells us where you are choosing your points xn, your sequence xn. And if we take a look at the pictures, this tells you where you can choose a sequence converging to your point. You can choose a sequence here converging to 3 from the right, or you can choose a sequence here converging to 3 from the left. That's what your S means. Let's write this down. The set S means where do you take your sequence? To define the limit using sequences. So this is where we can actually define all of the definitions simultaneously by using this general definition. And let's go to the last one. This is for infinite limits. So when your variable is infinite, of course, in all of these cases, L could still be either a number or plus infinity or minus infinity. But in this case, infinite means that your A itself is infinite. For a function f, we write limit as x goes to infinity of f of x is equal to L. So here's your infinity. L can be a number, or L can be plus infinity or minus infinity. If we have the original definition, for some interval S, we want to consider infinity here. We want to consider your sequence of points going to infinity. So, this is an A, this should be also infinity. But your interval has to be something going all the way to infinity. And similarly, we do the same thing with minus infinity. In this case, your set of points has to be something coming from minus infinity. So here are all the possible definitions. Let's see now some examples. To take, for example, limit x goes to 4 of x cubed. This is equal to, this is a continuous function. We already saw this. We proving that this is continuous. Well, this is something to the cube. We can use the limit laws, or you can use, yes, this is a polynomial from the assignment. If this is continuous, then we can just replace the value. 4 to the 3 is 64. This is continuous at 4. And limit x goes to 2 of 1 over x equals 1/2. Because x cubed and 1 over x are continuous at those specific points, 4 and 2. respectively. This follows from our continuity laws, or laws for continuity of functions. We know that x is continuous. One of our laws tells us that the inverse of a continuous function is continuous at any point that's not zero. So this is continuous here, so this is 1/2, and this is 64. So now, okay, what happens if we do take a point where this is zero, then this is no longer the case. One can see that the limit as x goes to 0 from the right of 1/x equals plus infinity. This is because we are talking from the right, so this means that our set is some open interval. So S is some open interval from 0 to something. So if you take a sequence of points converging to 0 in S, this just means that you have a sequence of points that are positive, x and greater than 0. So this 0 plus just means that their sequence is greater than 0 and it's converging to 0. And we have the limit law for sequences converging to 0 for the inverse. This means that 1/xn is converging to plus infinity by the infinite limit law for sequence. And what happens if we take the limit as x goes to 0 minus of 1/x? In this case, there's that s is something to the left of 0. So if xn goes to 0 with xn in S, this means that xn is less than 0. So here, x goes to 0 minus, this means that your sequence is negative. You're approaching 0 from the left. Here's how we are applying exactly the definition that we have here. We are saying that this is your set S. In this case, this is 0. So this is an interval to the left of 0. And this is what is important for us from that. And what this means, we cannot apply the infinite limit laws for sequences because this infinite limit law has as a hypothesis that your numbers have to be positive. So take a look all the way back. Here. This is the theorem for infinite limits of sequences. That's the one that tells us that something by 0 is infinity. It tells us that for a sequence of positive real numbers, so this is a hypothesis, then the limit of your sequence is infinity, if and only if the limit of the inverse is 0, but you need them to be positive. And here we don't have that. Let's go back. So in this case, they are negative, so we cannot apply the infinite limit laws. But it's easy to fix that. This is CRM 9.10, and it only applies for positive sequences. So here does not apply. But it's easy to fix it. Just consider the sequence minus xn, because if xn is negative, minus xn is positive. So now this is a positive sequence, and you can apply the theorem for this sequence here. So by the infinite limit laws, for this sequence, we have that the limit of 1 over minus xn is plus infinity. But we can just take this minus outside. This is something that you can check from the definition of infinite limit. If you take this minus outside, this means that the limit of 1 over xn equals minus infinity. You can show this from the definition. Here we are using the fact if Sn is a sequence in R such that Sn goes to minus infinity. So let Sn be a sequence in R. Say it like this. Then this is true if and only if minus Sn goes to minus infinity. You have to check this from the definitions because there's a different definition here than here, but you can check that this is true. This is what we are using here. So in particular, the limit to the right is plus infinity, the limit to the left is minus infinity. And this means that the limit when x goes to 0 of 1 over x does not exist, since the two lateral limits are different. We will justify this later. The connection between lateral limits and ordinary limits. Okay. You can see some more examples in the textbook. For now, I will move on to state some of the other properties. Of course, this example of 1 over x is a simple example, but the point here is to see how we can rigorously show what we expect to be true from the definitions using sequences and using the laws that we already proved. So now we can give a theorem for limit laws for functions. And again, they would be harder to prove if we had to use epsilons and deltas in each case, but they are very easy since we already know the limit laws for sequences. So let's just state them. Let f1 and f2 be functions. As always in this course, functions mean functions from a subset of R to R. And let's suppose that we have L1 equals the limit as x goes to a along S of f1 of x, and L2 equals the limit as x goes to a along S of f2 of x. So we have two limits. In both cases, we have the same a here, and we have the same set S. So we are stating it for the general definition. This means that this applies for all cases. This is why this is useful to have this general definition here, because then we can state theorems that apply for all of them, and we have even a general proof for all of them. So we have two limits, and we are assuming that they exist, and we are also going to assume that they are finite. No infinity here. Or at least the L itself is not infinity. Then we have to see a law for addition, for multiplication, and for quotient along the same set S. So the limit of f1 plus f2 of x exists and is equal to L1 plus L2. So when we're saying this, we are saying in particular that it exists. This is part of the theorem. This is for the addition, and the same thing holds for multiplication. Again, we are saying that this exists and is equal to that. And the quotient. This one needs extra conditions. So we're saying that this exists and is equal to this, provided, of course, that nothing in the denominator is 0, provided that L2 is not 0, and f2 of x is not 0 for x in S. So now we have these laws for addition, multiplication, and quotient. They have the natural conditions, and we are stating this with the set S. This means that this holds in all of the cases: ordinary limits, lateral limits, or infinite limits. So for example, let's prove one of them. This is just going to follow from the limit laws for sequences, since we already proved them. This is why it is good to define this using sequences. So by assumption, f1 and f2 are defined in S, and A is the limit of some sequence in S. This is part of the definition of this limit existing. And so f1 plus f2, f1 times f2, and f1 over f2 are defined in S. In this case, under the conditions that we have, provided that f2 is not 0 in S. So under our hypothesis. on their respective hypotheses. So now let's consider a sequence in S with xn converging to A. A could be a number, or could be plus infinity or minus infinity. And now we can apply the limit loss for sequences by the sequence limit loss. We have all of the hypotheses that we need. The limit, here we are at n goes to infinity, of f1 plus f2 of xn is equal to the limit, n goes to infinity, of f1 of xn plus the limit, n goes to infinity, of f2 of xn. This is the sum of these two sequences. We can take the limit of 0 to sum by the limit loss for the sequences, which we are assuming that this is equal to L1 plus L2. And this is what we wanted to show. And similarly for products and quotients. This is actually a proof of all of them. But here I'm writing explicitly the case of the sum, but the others are exactly the same thing. So the important part is that we already proved this. This is where all of the power lies. So this is for limits of sums, products, and multiplications. Another important case is for composition. It basically says you can put the limit inside of a continuous function. Here's the actual statement. Let f be a function for which the limit L exists. We are in all of the cases because we are using the general definition. With a set S. So it could be lateral, it could be two-sided, it could be infinite. And is finite. When we say here that the limit is finite, we are saying that L is finite, but A could still possibly be infinite. So A can be infinite. Here we are saying that the limit L is finite. So L is finite. Now we have another function G. Defined on the domain of the codomain of F. instead of points f of x, where x belongs to S. Since this is always with a set S, this is our set S, but now we are planning the function f. And it also has to be defined in L. And it has to be continuous at the point L. Normally, we don't need our function to be defined in A. F does not have to be continuous, but G has to be continuous. And it has to be defined in L, and it has to be continuous at L for the function G. And in this case, so we need stronger hypothesis here. This is why we are saying here, put the limit inside of a continuous function. The continuous function here is our G, not the F. Then what we can conclude is that the limit as x goes to a along S of G composed with f of x, this exists and equals G of L. In other words, we are saying that the limit of x goes to a along S of G of f of x equals G of L, which is the same thing as G of the limit as x goes to a along S of f of x. This is L, so this is L, so this is L. This is what I am saying, that here we are putting the limit inside of the function G. So we can put the limit inside of a continuous function. G is our continuous function. You can pass the limit inside, which this is what we're doing here. This is L, so this is G of L. This one is important to prove it. Let's prove this one. Let's copy this. So the proof is actually easy, and again, this is easy thanks to what we are doing with sequences. It will be harder to prove this with epsilons and deltas. To be able to show that a limit exists, again, from our definition, we need to show that we need to show two things. We need to show this and this. So first you need to show that your function is defined in S, and then you need to show this property about sequences. So this is why we need to show those two things. So the first thing is first, this function has to be defined in S. This is true by what we are assuming here. G composed with F is G evaluated at this point, so this is just true by assumption. So now we show the second part. So let Xn be a sequence in S such that Xn converges to A, which can be infinite or a number. then f of xn converges to L by definition, since this is the limit. And now, since g is continuous at L, by definition of continuity, we can apply g to this sequence. Then g of f of xn goes to g of L, which means just that g composed with f at xn converges to g of L. And this is what we wanted to show. This shows that the limit exists and is equal to g of L. So it follows from our assumptions. It's iffy using sequences. So for example, if you have that the limit of a certain function is equal to a certain L, then this means that the limit of the absolute value of the function is equal to the absolute value of L. Because in the section of continuity, there was a theorem that's saying that the absolute value function is continuous. So the function d of x defined to be the absolute value is continuous. So we cannot always just put a function inside the limit, but we can when the function is continuous. And similarly, say, so this only makes sense if L is finite, which is what the theorem tells us, but A can be infinite. And let's say that we have a function and we know some limits. Let's assume that the limit when x goes to 0 from the right, from the positive numbers. Let's say that this is 0, and that the limit when x goes to infinity of f of x is equal to pi over 2. Say you have a function with whatever function. It can do whatever you want here, we don't care, but to the right of 0 and to infinity, when x goes to 0, this goes to 0. Here is pi over 2. When x goes to infinity, it can do whatever here, but when x goes to infinity, it goes here to pi over 2. This can be your f of x. You just know these two facts. It goes to 0 here, and it goes to pi over 2 at infinity. These limits are finite, even though it is an infinite limit. But then we are under the hypothesis here. If we just choose some continuous function g, so it can be whatever. Then the limit as x goes to 0 from the right, but it has to be the same. Here we have 0 plus, then here we have also 0 plus. of, let's say, the exponential e to the f of x is equal to, and we can just apply the e in the exponential here. E to the 0 is 1, and limit as x goes to infinity of e to the f of x is e to the pi over 2. Similarly, limit when x goes to 0 of sine of f of x. Sine of 0 is 0. Limit as x goes to infinity of sine of f of x is sine of pi over 2 is 1. This is a continuous function, you can put it inside. This is a continuous function, you can put it inside of the limit. But it is important to note it's necessary for g to be continuous. So let's see a counterexample. I can show you a functions f and g such that limit when x goes to 0 of f of x is 1, limit when x goes to 1 of d of x is 4, but the limit as x goes to 0 of g composed with f of x does not exist. So, but the theorem will tell you if g were continuous, then this would just, the limit of g composed with f would be just g of the limit, but g of, or the limit. So what I'm saying here, limit as x goes to 0 of g composed with f of x. What we could expect is that this is, say this is, let's write it like this. We could expect that we can put the limit inside. Well, g is not necessarily defined, but it should be, since this is the limit of x is equal to 1, we expect that this should be the limit of g as x goes to 1. But this example tells us that this fails. Because our function is not going to be continuous. The example is the follows. F of x equal to 1 plus x sine of pi over x when x is not 0. And it can be whatever when x is 0. And that g of x equal to 4 when x is not 1, and minus 4 when x is equal to 1. Then for this example, we showed that this goes to 0 when x goes to 0 in a previous class. So this means that f of x goes to 1. When x goes to 0, and the limit when x goes to 1 of g is equal to 4. Since this function is constant equal to 4 as long as you are not 1. But now let's consider a specific sequence. Consider the sequence xn equal to 2 over n. Then f of xn. So this is a sequence going to 0. This is not 0, so f of xn, we can just plug that in. This is 1 plus xn sine of pi n over 2. And when n is even, this is going to be sine of a multiple of pi. So this is going to be 0 when n is even. So this is 1 when n is even. This is 1 when n is even. And when n is odd, it's not going to be 1. This is not going to be 0. When n is odd, this is going to be either 1 or minus 1. So this is just going to be 2 over n. And this is just going to be 1 plus or minus 2 over n. So this is just something that's not 1 when n is odd. This means that g composed with f at xn, this is 1 when n is even, so this is g of 1 when n is even. G of 1 is minus 4. Minus 4 when n is even. And it is something that is not 1 when n is odd. When it is just 1, this is 4. So this is 4 when n is odd. This means that xn converges to 0, but the limit of g composed with f of xn does not exist. So this means that this shows how we cannot always plug in the function g inside of the limit. This is neither 4 nor minus 4. It is oscillating, so it's neither of them. We cannot just put the value of g inside, and we cannot just take the limit outside. So this is a counterexample to show that we really need g to be continuous. The reason why this fails is because your function g is not continuous. which is why the limit then does not exist. Okay, so let's take a look at what we've done so far today. If we go back to the list of topics that we want to say about limits, we showed different types of limits corresponding to these pictures. We gave a rigorous definition, a general definition that encompasses all of them, and we showed how to specialize that definition for each specific case. And those are the standard definitions. We gave the function limit laws, including the laws for addition, product, and quotient, and the law for composition. And we can stop here for today. Next time we'll talk a little bit about this epsilon delta characterization of limits, how it is equivalent to what we're saying, and we will use that to show how lateral limits imply that the ordinary limit exists. And with that, we'll finish limits with the goal of then going to derivatives.